All right, today we are diving into the hidden language that connects, well, pretty much everything, from your social media feed to the very structure of the internet itself.
Think about it for a second. Your friends, the entire internet, a map of a city. What's the connection? Well, they're all networks. And the mathematical language we use to describe them is something called graph theory. It's like the invisible blueprint for so much of our modern world. And today, we're going to make it visible.
So, where do we even start? Let's break this down to the absolute basics. Every single one of these complex networks, no matter how huge, is built from just two incredibly simple components. First things first, we have the vertex. You can also call it a node. All it is a single dot. Seriously, that's it. Now, that dot could represent just about anything: a person in your friend group, a city on a map, or a single web page. Okay, now let's take two of those dots and just draw a line between them. That line, that's called an edge, and it represents the relationship or the connection between those 2 points. So a friendship, a road, a hyperlink on a website, you get the idea. All of those are edges. And when you put it all together, a bunch of vertices and the edges that connect to them, you officially have what we call a graph. This simple structure, which we write out as G equals VE, is the absolute foundation for how we map and study all kinds of networks.
All right, so we've built our graph. Now what? What's the first thing we can actually learn from looking at it? Well, we can start by measuring how important or connected a single point is, and we do that using something called its degree.
The degree of a vertex is just a super simple count. How many lines or edges are touching it? That's it. You know, in a social network, your degree is basically your friend count. It's the most fundamental measure of how connected you are.
Now here's where it starts to get interesting. If you look at this table, you'll see we can classify vertices by their degree. So vertices A and B have an even degree, right? 2 connections each. But C and D have an odd degree. This might seem like a small detail, but it's actually the key to solving some really famous problems, like figuring out if you can trace a shape without ever lifting your pen from the paper.
And that leads us to this really elegant rule with a fantastic name, the handshaking lemma. It says that if you add up the degrees of every single vertex in a graph, the total will always be exactly double the number of edges. And it makes total sense when you think about it. Each edge is like a handshake connecting 2 vertices, so each edge adds 1 point to the degree count of 2 different vertices. It's just a simple, powerful piece of mathematical truth.
Okay, now that we have the building blocks, let's take a little tour of the zoo of different graphs out there. Because not all networks play by the same rules, and these little differences are absolutely crucial for understanding how things work in the real world.
So a connection can be a two-way street or it can be a one-way path. In what we call an undirected graph, an edge between 2 people means they're friends. The feeling is mutual. But in a directed graph, that edge has an arrow. It's like following someone on social media who doesn't follow you back. The connection only goes one way.
Next up, we've got simple graphs versus multigraphs. A simple graph is, well, simple. It only allows one connection between any 2 points. But a multigraph lets you have parallel edges. Think about all the different airline routes that connect the same 2 cities. That's a perfect real-world example of a multigraph. Now for a really fascinating special case. What if you have a graph where every single vertex is directly connected to every other vertex? Nobody is left out. This kind of super-connected network is called a complete graph. Let's see how this thing scales. The simplest possible complete graph, which we call K3, is just 3 vertices all connected to each other. And as you can see, it makes a perfect triangle. But watch what happens when we add just one more vertex to get K4. The number of edges jumps from 3 all the way to 6. Each of the 4 points now has to connect to the other 3. The whole structure is already getting way more dense.
And by the time we get to K5, you can really feel the complexity just explode. Every single one of these 5 vertices now has a degree of 4. This kind of exponential growth in connections is such a crucial concept in network analysis. It tells us just how tightly knit a system can become.
So, okay, dots, lines, triangles, this is all cool math for sure. But why is this abstract language so incredibly powerful out here in the real world?
Well, because as you can see here, graph theory is literally the backbone of modern computer science. When Google Maps finds you the best route, it's actually finding the shortest path in a gigantic graph of roads and cities. When a social network recommends a new friend, it's analyzing a massive graph of your social connections. This isn't just theory. It's the code that runs our digital world.
So now that you understand these basic building blocks, you've basically gained a new lens to see the world through. These structures are everywhere, in biology, in logistics, in how ideas spread. The real question I have for you is, now that you know the secret language, what hidden networks are you going to start seeing all around you?